Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at various types of pressure sensors. In this video, we will look at capacitive pressure sensor. What is the principle of operation of a capacitive pressure sensor? What are the key characteristics of the capacitive pressure sensor, and how do we convert the signal from a capacitive pressure sensor? Recall, in one of our previous videos we did discuss this in brief. Here we expand on that previous discussion. I think in week 2 we discussed how this works in one of the previous videos. The principle remains the same. Here we expand on that previously discussed concept. Recall that if something is discussed more than once, in particular if something is discussed 3 times, for example, it is important. It is very important for your learning and also from the exam point of view. So, the idea is that there are 2 electrodes that form a parallel plate capacitor. In a capacitive pressure sensor, there are 2 electrodes that form a parallel plate capacitor. For example, like this. One of them is rigid, the other one is a flexible diaphragm. We need to choose the stiffness of the diaphragm such that it is suitable for the range of the pressures that we are interested in measuring. That is, in the pressure range that is used, this diaphragm must bend or must deform. At other pressure ranges, it would better not respond. So, this diaphragm deflection, when a pressure is applied, essentially changes the distance between the 2 plates of the parallel plate capacitor. Recall that the capacitance of a parallel plate capacitor is epsilon A by D. In this, epsilon cannot be changed. Well, actually there are designs in which epsilon r can also be changed, but in this case we are focusing on the principle by which epsilon or the dielectric between the 2 plates is the same, the area of contact is the same, and the distance between the 2 plates remains the same. Recall that in this particular case we are discussing epsilon A by D, in which epsilon remains the same and the area remains the same, and it is only the separation between the 2 plates that changes. How would it change? Why would it change? When a pressure is applied, this flexible diaphragm deforms and changes the distance between the 2 plates, thus changing the capacitance. And I could measure the output voltage across the capacitor, thus attempting to model what the distance would have been that could have caused this change in voltage, which was caused by a change in capacitance. So, what we are measuring is voltage, measured voltage, and this voltage change is caused because of a change in capacitance, and this capacitance change is caused by a change in distance d, separation between the plates, and this distance d is caused due to a change in pressure. This is the principle of operation of this capacitive pressure sensor. We could oscillate or power this capacitance or capacitive pressure sensor using an internal AC oscillator and a demodulator that extracts the output or the diaphragm deflection signal. Now, the output voltage and the input voltage will be of the same form So, the time varying output signal will change according to the changes in the pressure, according to the changes in the distance, which means that according to the changes in the pressure. In this, Vi is the input voltage or the excitation voltage, and omega is the angular velocity of the oscillator. We have given these two things here. What are the advantages? The advantages is that these are really small. They can also be realized in semiconductor circuits. They can be miniaturized in a very big way. So, they are very small. They are also low power devices, and so they are suitable for measuring pressure in implanted systems. So, these are some of the advantages. But some of the challenges are that it requires an oscillator and a demodulator circuit to study what the distance is, what the displacement is. So, this means that there is a possibility of having a higher noise and a reduced bandwidth. Now, reduced bandwidth is a challenge with this kind of sensors. So, in comparison with piezo resistive sensors, we look at piezo resistive sensors in a different video. In comparison with piezo resistive sensors, the bandwidth or the range of pressure through which this sensor will work is smaller. So, the current work in this field involves the development of MEMS and NIMS based sensors and AI enabled interpretation, that is having AI as part of the circuitry that will decide whether a pattern of pressure is anomalous or healthy, for example. AI enabled pressure detection or pattern detection. Using these as part of a feedback loop that enables early or preventive clinician interventions. So, a pattern of pressure is detected that is considered anomalous or unhealthy or dangerous, then the system can alert the clinician saying that a patient in this bed is having this problem, this pattern. Then the clinician can take an appropriate decision, for example. This is the current work and the future in this field. With this, we come to the end of this video. In this video, we looked at the principle of operation of a capacitive pressure sensor, how is a signal converted and read, and what are the key characteristics of a capacitive pressure sensor. We also looked at what is the current and future development in this field. With this, we end this video. Thank you very much for your attention.